Good morning, everybody. Welcome to Stat 201. This is week 4, and we didn't meet last week because of Columbus Day. But here we are back at it, and we've got some fun, exciting things today that hopefully will help you understand better about probability, because that's the first part of what we're doing in this course. Once we understand probability, we can then start talking about statistical inference and building upon the rules and laws of probability. So when we talk about probability, what are we talking about? What is probability? Probability equals the study of uncertainty, right? So what does it mean to have something that's uncertain? It means you don't know what the outcome is going to be for whatever reason. So there's an interesting web page that I want to bring your attention to, and we're going to look at it just real quickly. Maybe you saw it already. It's in the week 3 folder, and had we met last week, we would have done this. But it's this ESP experiment, and Clifford Pickover has written a lot of books. And so if you go to that in the week 3 folder, the first link there, I guess it's the second link, first link, yeah, under the task list. He's conducting an ESP experiment. What is ESP? Extra sensory perception. So what does that mean? He's trying to determine whether you can communicate non-verbally or not using body language, just with your brain, with your mind. What do you guys think about that? Is that possible? No? No one has any thoughts or ideas? Did you guys have a good weekend? Everybody had a good weekend? Everyone had a good week? You didn't have to come here last week? Anybody do anything fun last Monday, Columbus Day? Anyone besides me? No? No one went kayaking? No? No one went windsurfing? No one went... let's see, what else did I do that day? No? You just did homework? Everyone's very quiet today. That's okay. That's good. Maybe you have the power of ESP, and you can communicate with your friends non-verbally, and maybe you're doing that right now, saying how lame this class is. But it's not. So this Clifford Pickover guy did this ESP experiment. So here is how the experiment works. You click on here. So what you need to do is look at these 6 cards right here. Everybody can see these 6 cards, right? So the instructions say there are 6 small cards below. Do not select your card by clicking on it. Instead, please say the name of your card out loud so that you can remember it. Now, everybody's going to have their own card, so don't say it out loud. Just say it out loud in your head, and then stare at the card. Okay, just stare at whatever card it is that you have picked, and when you've committed your card to memory, I'm going to click the blinking eyes down here. Okay, so everybody knows what card they're picking individually, right? Everyone good on this? Okay, now this is where the magic comes in. This is the ESP experiment. Is your card still there? The rest of the cards still there? How did he do that? Now hold on. If you know, don't say it quite yet. But if you're just wagering a guess, then go ahead. Oh, so you do know. All right. So he changed all the cards, right? You were only staring at one card, and then that one disappeared. But all the other cards, so if you go back, I think you can see exactly what he had there before. Is your card there now? Should be the same group of cards. Now we've got a King of Hearts, a Jack of Clubs, King of Spades, Queen of Diamonds, Queen of Clubs, and Jack of Diamonds. So what do you see now? None of those cards. They're just replaced with other face cards that have the same pattern as red, black, red. And so what's going on here? Is this really an ESP experiment? No, it's not. This is a classic tale of somebody trying to do what? Trick you. They're trying to make you think that they understand randomness and uncertainty and that they can predict the future. Can they predict the future? No, why not? Why can't they predict the future? Because there's only one way to predict the future. Did you guys watch this video that I have in week 3 folder here? Right here, How the Amazing Spider-Man 2 should have ended. Did you guys watch that? No? Should we watch it right now then? Okay, we'll see if the sound works. Let me turn this up all the way. And I've got to push pause on the recorder. Otherwise, it will kill everything. It's pretty funny. Yeah? What does that have to do with Clifford Pickover and his experiment? You guys want the lights on or off? On? Off? So what does it have to do with this? Clifford Pickover and his ESP experiment. Okay, imagine you get an email from somebody that you don't know. You've never before heard of them, you've never met them, but they say in their email the Apple stock is going to go up next week. And you say, maybe it will, maybe it won't. And then you wait a week later, and what happens to Apple stock? Sure enough, it goes up. Okay? And you're like, it was a lucky guess. What are the chances? And you could say what the chances are. What are the chances? They got it right. 1 out of 2. It either went up or it went down. Okay, so that's the first email. The next week you get another email, number 2, and it says Apple is going to go down this week. And so you wait, and sure enough, the Apple stock goes down. And you say, well, what are the chances? You say, well, it's 1 out of 2, but what are the chances they got it right 2 weeks in a row? That's 1 out of 4. Right? And if you don't understand where the 1 out of 4 comes from yet, we'll talk about the binomial distribution, which is something you can use to calculate probabilities like that. What do you think happens in week 3? You get another email that says Microsoft is going to go down this week or next week. At some point in the future, Microsoft's going to go down. And what happens to Microsoft? Sure enough, it goes down. So these guys are right 3 weeks in a row, and you still say, okay, 1 in 8 chance of that happening. What happens after you get 10 emails from these guys,
And they're right every week, and then the final week they say Microsoft is going up. So they've gotten it right 10 weeks in a row. What are the chances of that happening? That they're just guessing. What are the chances if they guess? 1 over 2 to the 10th. Okay, so the probability of all 10 correct is equal to 1 over 2 to the 10th. What's 2 to the 10th? So this is something you guys need to have committed to memory. All the powers of 2 from 0 all the way up to 10. And I'll show you why you need all of those in just a minute, but I think you know it. 1024. So this is about 1 in 1,000 or 1 in 1,024 chances. So are they guessing? They got this right 10 weeks in a row. What are the chances they're guessing? Very low. 1 in 1,000. So what's the next email going to say? What do you think? Are they going to tell you what's going to happen to some other stock? Week 11? No. They've got you at this point. You're thinking, these guys are really good. For 10 weeks, they told me exactly what's going to happen. In week 11, they're not asking me to check stock prices. They're asking me, hey, look at our track record. Don't you want to invest with us? We can take your money and we can multiply it by the power of compound interest in stocks, bonds, and all financial instruments that are out there. Doesn't that sound pretty good? You want to go with these guys? Well, turns out they're lying to you. How are they lying to you? Why are they lying to you? How do you know they're lying to you? Just like Clifford Pickover tricked you into thinking that he was able to read your mind from who knows where he is. These guys are lying to you. How do they do it? Well, what's the only way that you can know exactly what's going to happen next week? What's that? Okay, but if you can't travel through time like Superman can, by going faster than the speed of light, how can you know? You can't. That's the point. Uncertainty, randomness, those are things you cannot predict. So if somebody comes along and tells you, hey, I can predict the future, and I did it perfectly for 10 weeks with no mistakes, you know they're lying. So how do they do that? Is this difficult to do? No, it's easy to do. Everyone can do it. So the first week, they sent out an email to you that said Apple stock is going up. But they also sent the same email to 500,000 other people. 499,999 other people. And then they sent almost the identical email to another 500,000 people that said what? The stock's going down next week. So after the first week, they have 500,000 people who think, they got the first week right. Lucky guess. And then we cut that in half the next week. We say, okay, now we have 500,000, or start with 10 million if you want. However many you want. I mean, it's the electronic age we live in. You can send out as many emails as you want. And some are going to go in the trash bin, or junk mail, and that sort of thing. But some are going to get through. The next 250,000 are going to say Apple stock's going up, and the other 250,000 say Apple stock's going down. So every week, they're sending out half as many emails as the week before. And so if they start with 1 million emails, by the time they get to week 10, how many people think they know what's going on. Well, it's about 1,000, isn't it? 1,000,000 divided by 1,000 is 1,000. So, in week 10, you got 1,000 people saying, hey, these guys are spot on. I mean, look at theirs. I got all the emails in my, my inbox, and I can go back and look at these things, and they're amazing. And now I'm going to take my life savings, and I'm going to invest with them. And then what's going to happen? Then they're going to buy that Ferrari that they always wanted and move to the Cayman Islands, or probably they're already in the Cayman Islands, and you're never going to see or hear from them again, and you're never going to see your money again. Right? So let that, hopefully this will sink in, that you can't predict randomness. So this is a random thing. These guys are saying, okay, here's a random process, and we're able to predict it. Now, you might get lucky and guess the outcome a bunch of times, but you can't predict it. And that's the definition of randomness. That's the definition of uncertainty. That's what we're talking about. Okay, so 2 to the 10. Why is it important to know what 2 to the 0 is? 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8, 2 to the 9, and 2 to the 10. So we already said 2 to the 10 is 1024. When you write these things out, it's pretty easy. 512, 256, 128, 64, 32, 16, 8, 4, 2, and 1. Well, this is the basis of binary digits. If you look at the sequence of binary numbers, the exponents can be used to come up with any number that's out there. But what if you're on a beach in a desert island somewhere, you're stranded, and you finally figure out that you can get off the island, get home, if you can come up with a quick approximation of the number 2 raised to the 24th power. And you got to do it quickly, like in 15 seconds. How are you going to do that? Anybody? I have a brother. I have lots of brothers, but one of my brothers works doing top secret stuff. He's a computer scientist guy, and works down in Virginia, I guess it was in Virginia. And so on his resume, he puts, consulted for such and such a company doing stuff, because you can't say what he's doing. And then he consults, the next line says, some other company doing stuff. And his resume's out there, and some guys at Google saw it and thought, oh, that's funny, that's cute stuff. Why don't we call this guy up and see if we can do a phone interview with him, and see if there's any interest in coming to California and whatnot. And so they called him up and they said, hey, we want to interview you. And he said, okay, fine. So they asked him, one of the questions in the interview was this question. You got 15 seconds to figure out a rough but accurate approximation to the number 2 to the 24. So you have time to go 2 times 2. We got 2 to the time to go all the way up to 2 to the 24. No. Now someone had their hand up over here. Well, what would you do? Or what would you have a comment, question?
I would just exponential that 2 to the power 10 times 2 to the power 10 would be 2 to the power. We equal to 2 to the power 20.
Okay. So you're saying, let's write this as 2 to the 4th power times 2 to the 10th times 2 to the 10th, like that? Okay. That's good intuition. Everybody see why you would think like that? Because 2 to the 10 is how much? 1024, which is about how much? It's about 1,000. So this is going to be approximately 2 to the 4. Well, once we memorize this, we know that 2 to the 4 is 16. So 16 times 1,000 times 1,000 is about 16 million. And so if you can learn to think about powers and exponents, which is hard to do for the human brain, you can write this down very quickly and say, oh, 2 to the 4, that's 16. 2 to the 10, that's about 1,000. Okay, so what if you had 2 to the 63? What's that equal to? Approximately. This is going to be 2 to the 3rd power times 2 to the 10th, 2 to the 10th, 2 to the 10th, and we've got 6 of those things. So this is about, that's equal to, but this is about 8 times 10 to the, what? 10 to the 18? All right, each of these 2 to the 10ths is about 3 zeros behind 10 to the 3rd. Okay, so that's very useful. Anyway, you can come back here and say, well, you know, if they do this for 20 weeks, what are the chances they get it right for 20 weeks? About 1 in a million. Okay, is that hard to do? How do we get a million? How do we get a million? Or how many do I have to start with so that I have a million people at the end of 20 weeks believing that I know how to do this? Well, we can figure out the math fairly easily, can't we? We started with 1 million people. We ended up with 1,000 after 10 weeks. So after 20 weeks, we started with 1 million people. We would end up with just one person. So multiply that by 1,000. So we need 1,000. So we need to do 1 billion. We need to send 1 billion emails out. Is that possible? I don't know. Probably not. 1 billion emails. That's a lot of emails to send. Okay. So questions, thoughts, comments. I mean, we need to have some sort of discussion about some of this mathematics stuff. It's kind of cool, isn't it? When you think about it and see how and where it applies to life. Well, counting methods are really based on what's called the multiplication rule. And you learned how to count when you were little, and you just said, okay, whatever integer I'm at, let's add one more to that, and you can do that forever. But the multiplication rule says if I have two different processes or sub-processes of a larger process, and I want to know how many ways I can complete that, I just have to say how many ways can I complete the first sub-process. So how many ways can I send out an email saying the Apple stock is going up or down? Well, there's 2 ways that can happen. And then the second process the second sub-process has 2 ways for that to happen. And we do that however many times, and we get 2 raised to the 10th power. Okay, so that's the multiplication rule. And this is the foundation for all sorts of other counting ideas and rules, including combinations and permutations. And I want to talk about permutations and just ask you a quick question. So by my count, I think there's around 47, 48 people in this classroom. Okay, so I have access to all sorts of information, but this is not one that I have access to. In fact, I don't really have access to that much information, but I want to know what you guys think is the probability that at least 2 people in this room have the same birthday. That's day of the month and day, not year. Okay? So if we have, say there's 45 people, what's the probability at least 2 of us have the same birthday? So think about this. What do we mean by probability? Probability is a number between 0 and 1 that tells us how likely the outcome of an event, the outcome of an experiment is. Okay, so you're going to put your answers in. I don't want anybody else to see what everybody else is thinking. So you can see in the bottom right corner we've got 3 responses. If you think, I want this in decimal format, so proportion, not probably, or not percent.
How many people were missing?
Yeah, 48. Oh, and by the way, you're not supposed to look this up and plug it into a calculator. We'll do that in a minute. I'll be astounded. But one thing I want you to think about is how hard it is to make assessments like this just by the seat of your pants. Right? You walk into an interview. I have another brother who's a banker, and he went to an interview and they said, "See those 2 people over there? What's the probability they're born on the same day of the week?" And they wanted to see if he could figure out the probability of that happening, and he did, and he said, "Okay, if that's the probability, then how much would you be willing to bet that those 2 people were born on the same day?" What do you think he said? "I'm not going to bet you because you picked the 2 people." Now, this is investing, this is Wall Street. There's all sorts of shenanigans going on. And so if I pick the 2 people, then then we'll talk about the probability of making a bet. But if you're picking the people, how do I know you haven't set this up in advance? This is your workplace. You probably know those 2 people. You have access to the records. You know what days they were born on. Okay, so how many responses? We only got 22 responses. I need more than that. I know you guys are all out there with your devices. You're going to have an opportunity to make a bet with me, if you like, in just a few minutes. But I know we got more than 26. What do you think? You got 45, 48 people, 50 people in a room. Probability at least 2 of them have the same. Then we're going to calculate that probability, and but before we calculate it, you'll have the opportunity to engage in a wager if you like. So we've got 31, and I'm going to call that right now. Let's look at the results. But if you did not answer, be prepared to answer the next question, because it will be easy. Okay, so we have the following. 100 times 1 over 2 times 365. About 1 in 10,000. That's about 1 in 10,000 as well. Or no, that's about 1 in 5,000. Is it 50,000? I don't know. So small numbers, small numbers. All right, so we got right here 1%, and then 1.5%, 2%, 3%. Finally, we get up to 25%. And then we have some people who put it in percentage form. So 11.5, 20, 20, 20. I'm not sure what does 125 mean. Is that 125% chance? Or is that supposed to be an eighth? So 0.125. I don't know. Okay, so here's the bet that I am going to offer to you guys. I think that at least 2 of us have the same birthday in the room. And the reason I think that is because not because of any information that I have about you guys specifically. I didn't go look through your records. I don't care when your birthdays are, other than
for this demonstration here. So if I'm right and you want to bet against me, no, if you're right and you bet against me, so if you think that nobody in this room shares a birthday, then you get the following to have happen. You get an A in the class. You don't ever have to come to class again. You don't have to take any of the exams, none of the quizzes, none of that stuff. If I'm right, almost exactly the same thing happens. You don't have to come to class again. You don't have to take the exams, quizzes, none of that stuff. But instead of an A, you get an F. Okay? So everybody understands the bet. Who wants to take that bet? Now, if I'm looking at this and I see 1 in 10,000, or 1 in, is that 5,000? I don't know, it's 50,000, isn't it? 1 in 50,000. 1 in 10,000, that's a really small chance. If you really think that's the probability, your hand should be in the air. I will take that bet. No one's going to take it. Get one? One person, okay. All right, well, before we reveal what the actual probability is, let's go to this next question. And please tell me what your birthday is. Now make sure you get the format correctly. So month and day. Just write the whole month out. And I have misleading instructions here. Don't write the whole month out. Put the first 3 letters of the month, and then the day, and yeah. So this should be an easy question for everybody to answer. Don't want the year, just want the month, and alphanumeric, and day. I'll send in my birthday too. I don't want anybody to say, hey, she has the same birthday as me. Okay, so we got 41, 42. No, we have more than 42 in here. So I'm holding out.
Try to put in the B, so you don't.
Sorry,
Try.
Okay, anybody else having trouble?
Did it take it? Oh, looks like 44, so maybe we're good. We'll just stop at that then. Although I really think we have more than 44 here today. All right, raise your hand if your birthday is December 5th. And who's the other person? Oh, it's the same person. Ah, dang. That would have been like so easy. Raise your hand if your birthday is August 27th. You're getting an A in the class. Probably. Well, I mean, if you earn it. Let's see. What else have we got? January. What, did I miss one? January 30th. January 30th, raise your hand. Well, if you did, and so did you guys know that you have the same birthday? Is that not amazing? It's totally astounding, isn't it? Have we got any other matches here? July 16th, raise your hands. Did you guys know that beforehand? Is that amazing or not? It's a small world. Okay, what else have we got here? September 19th, raise your hands. Did you guys know each other? Did you know you had the same birthday? One time I did this with twins, and they were obviously, I mean, that wasn't easy. No one took me on that bet that day. Let's see, was there any other? We had April 27th. There's only one person born in April. Okay, so what's going on? Why is that? Why would I even make that bet? Who's the one who bet me?
We should have a talk after
During the break. How can I find this probability? Is this a hard probability to find? Probability. Let me move to the next page. Probability at least 2 shared birthdays. How do I find that probability? Well, the easiest way to do probability calculations sometimes is by looking at the complement of the event. In other words, if I looked at the probability that at least 2 of us had the same birthday, well, there were 3 pairs in this room with the same birthdays, the shared birthdays, but none of them shared birthdays with the other pairs. So that's one way it can happen. But we could have had 3 or 4 or 5 or a whole bunch of other pairs of shared birthdays. In fact, how many different pairs are there if you have a group of, say, we have 44 that answered. If I have 44 people, how many pairs? In other words, if we had a party that we went to and everybody shook everybody shook everybody else's hand, we'd say, how many unique handshakes are there? Well, the first person shakes how many hands? 44. Sorry, 43. You're right, 43. Right, you can't shake your own. I guess you can shake your own hand, but that's not a unique handshake. So you're right, 43. So we have 43 handshakes. Let's write that over here. How many does the second person shake hands with? 42, right? Because you're already counting the handshake they had with the first person. 42. And then the person before that, 41. All the way down to the last person doesn't shake anybody's hand, but the person before that shakes one person's hand. So if I wanted to add up all of those numbers, how would I do that? Well, I could get my calculator out and I could type 1 plus 2 plus 3, or I could use a spreadsheet and put in the sequence 1 up to 43 and tell it to sum. Is that hard? Is that easy? If you're Gauss, you guys know who Gauss is? You ever hear of Gauss? He was a German mathematician, and he was one of those genius people when he was a kid even. And the story goes, he was in class and extremely bored, and so he was rambunctious, got himself into trouble a lot. And the teacher said to him one day, knock that off, whatever it is you're doing, you're just causing problems, you just lost recess. So recess comes along, everybody else is up for recess, and they get to play and have fun. And he's sitting there thinking, how long do I lost recess for? And the teacher says, well, look, I'm not all that bad of a guy. I'll give you an opportunity. If you do some busy work, then you can earn recess back. So add up the numbers from 1 to 1,000. That's all you have to do.
and then you can go outside. And if you can do that in the next 15 minutes or 20 minutes, then you can go out and enjoy your recess right now. But if it takes you to the next recess and the next recess and the next recess, the teacher thought he'd come up with this clever way of punishing Gauss. So what did Gauss do? He took his slate and he wrote on it in chalk 5,050, handed it to the teacher and said, "I'm out of here." How did he know that? How would you do something like this in a quick manner? Well, if you take the first number, which is a 1, and you take the last number, which is 43 in this case, you add those together, what do you get? 44. If you take the second number and the second to last number, and you add those together, what do you get? 44. 3 plus 41 is 44. So if you do that enough times, then you've added all the numbers together. So all you really need to do is say what's the first number plus the last number, and divide that by what? Sorry, the first number plus the last number. How many of those do you have? So this is going to be 44 times, how many 44s do I have? Well, here's the formula. It's 44 times 43 divided by 2. And maybe we should have had an even number here instead of an odd number. It would have made more sense. But nonetheless, that is the formula. So if you're taking the summation of well, let's see, we're going to write it like that. You're adding up the numbers 1 plus 2 all the way up to n. This is going to be n times n plus 1 divided by 2. Okay, have you seen that before? Where have you seen that? Combinations. If I have n objects, and I'm choosing 2 of those, n choose 2, that's going to be n factorial divided by 2 factorial divided by n minus 2 factorial, and that's just n times n minus 1 divided by 2. Okay, so this is an application of a combination, except for instead of n we have 44, right? 44 people in the class. How many pairs are there? That's the same as saying I'm adding up the numbers 1 to 43. So what I'm talking about really is the same thing, although the formulas might look a little bit different, because here I'm saying, oops, if n is 44, then I have 44 times 43 over 2. But here I'm adding up 1 to 43, which is the same thing as saying how many pairs are there of 44 people. Okay, interesting, isn't it? Yes, it's certainly interesting, but how does that help us understand the probability of at least 2 of us having the same birthday? Well, the point is, if I use the law of complements, then all I have to do is count the number of ways that I have no shared birthdays. And that's a lot simpler than counting the number of ways that I can have pairs, or triples, or quadruples, or quintuples. I mean, I can do that. There's a systematic way to do that, but it's really really confusing and convoluted, and you don't want to do that. Instead, you want to say, what's the probability of no shared birthdays? Well, what's the probability of no shared birthdays? We have 1, 2, let's just, let's get a new sheet here.
So 1 minus the probability of no shared birthdays. That's 1 minus. How many ways can I have 44 people have a unique birthday? That's the question. So the first person that I'm interested in, or the first person in the room that we select, we would say how many days can they be born on? We're going to ignore leap year. And you're going to say, well, there's 365 different days that they can be born on such that nobody else has the same birthday as them, because they're the first person. And then we're going to say, okay, the second person can be born on how many different days? And it turns out to be 364. Right? Because the first person was born on whatever day they're born on, so the second person has less days to be born on. 363, and so forth, all the way down until the last person in the room, which is going to be 365 minus 44 plus 1. Okay, so that's the number of ways that we can have unique birthdays. Is that a big number? Yeah, it's pretty big. Turns out that there's a special name for that. It's permutations. So permutations of 365 objects, chosen 44 at a time. Now that's just the numerator. That's a big number. And so now we have to count the number of ways that we can have 44 different birthdays where there are no restrictions. That's going to go in the denominator. So think of the classical approach to probability, which says all the birthdays are equally likely. And so if that's the case, then the first person without restriction can be born on 365 different days. And then 360 for the next person. How many days can they be born on? 365, right, without restriction. Anyone can be born on any day of the year. So we have in the denominator 365 raised to the 44th power. So which of those numbers is bigger? The one in the denominator is much bigger. In fact, if you come back over here to the week 3 folder, you'll see the birthday problem generator. The link right down towards the bottom. You can come in here and say, if I have 44 people, just slide that up to 44, I can calculate the probability, and the probability is 93.28%. That's pretty high, isn't it? So, do you think I was really risking giving anybody an A that didn't deserve it? Sure, there's about a 7% chance of that happening, or 6.5. What if there were 48 people in the room? It goes to 96%. So you should get on and play with this because it's kind of cool to see. If I have, say, 100 people, or thereabouts, what's the probability going to be, do you think? 99.999%. Now, if you don't believe this, you can actually take a sample and click that button, and it generates a bunch of random birthdays and highlights all of the pairs. Sometimes there's triples. Here's a triple right here, 1115. There's 3 people. And you can do it again if you want, and again and again and again. You'll see that every time you do this, you're getting matches. If you do it 5,000 times really quickly, click this button, and it will say, even out of 5,000 attempts, we still didn't have any samples where there were no shared birthdays. So what number do you have to have in order for the probability to be 50%, you guys think? If you had to just guess a number. Imagine you go to a party Friday night, you get your stat quiz done, and you say, all right, how many people need to be at this party before I'm going to start taking bets on whether we share birthdays? And someone said a number, right? What did you say? 18, okay, is that, well, let's just go over here and see, is 18 the right probability? 18, what's the probability if you have 18 people? It's 34.69%. If it's not 18, you can use this. Turns out if you have 23 people, probability is a little over 50%. Is that intuitive to you guys? Counterintuitive? I didn't see anybody who said they thought the probability was that high. Although somebody said 125. But when you understand how these things can be calculated, then you can make better decisions. Right? But if you knew the probability was 93% that at least two of us had the same birthday, no one would have taken me up on that bet. Even though there was a chance that you would get an A in the class for taking the bet. Very unlikely anyone would do that. Okay, so again, you can take samples, and in the long run, if you take 5,000 samples, for example, this number here should converge to the true value of 50.72%. Okay, so questions, thoughts, comments? Is that cool? That's cool, isn't it? Yeah, that's cool. All right, we're going to take a break for 10 minutes. When we come back, we're going to look at one more example of how you might use information in a way in which is most beneficial to you. And then I will answer any questions you have about homework. There's homework number 3 is due on Thursday. That's the chapter 5 stuff. And that's due on Thursday, right? Yeah. And then next week you can ask questions about homework 6 if you want. So break for 10 minutes. When we come back, we'll do something else that's fun that I think. Let's do that then. Okay, so we found out the probability that at least 2 of us have the same birthday was 93% or thereabouts. And so hopefully one of the points I want you to take away from this is that being able to assess the probability of events is not always easy. And if you do it from, kind of flying by the seat of your pants, oftentimes, if you're just pulling numbers out of thin air, you're going to be wrong. And so you don't want to base decisions on that. You want to be able to think things through and actually write down what the probability is and how you think about the question determines, of course, the outcome. So here's an example of the use of Bayes' theorem. So Bayes' theorem says if I have the probability of an event A that I'm interested in, unconditionally, so if I don't condition on anything else, I have what's called the unconditional or the marginal probability of the event A. But let's say there's some other event B that comes along, and I know that B has happened. Now I want to update the probability that the event A is going to take place, or has taken place. So I do that by writing the probability of A given B being equal to the probability of B given A times the probability of A, all of that divided by probability of B. Okay, so notice that up here in the numerator I have the unconditional probability of A, or sometimes it's called the prior probability of A. Excuse me. So this is called the prior probability of A. And if that's the prior probability, then this is called the posterior probability of A. So what I have on the left-hand side, probability of A given B, that's the posterior probability. And what I have on the right side is the probability of A, or the prior probability of A, multiplied by some other stuff. And to see where this formula comes from, you can look at the multiplication rule, which says the probability of the intersection of two events is just equal to the conditional probability of one event times, given the other event, times the unconditional probability of the conditioned on event. Right, so you can say the probability of A intersect B is equal to the probability of B given A times the probability of A, but it's also equal to the probability of A given B times the probability of B. And so I solve that for the probability of A given B, and I get Bayes' theorem. So what does this mean? This means as information comes along, usually I can update my assessment of the probability of the event of interest. So if you're going to cross Market Street over here, if you were to just randomly walk across the street with your eyes closed, what are the chances that you're going to get across the street? Anyone? I have no idea, but it's not a good idea, is it? Because if there's cars going down the street, good chance you're going to get hit and die. So what kind of information would you want to know about? Well, you'd open your eyes and you would see there's a walk, the little white guy walk signal that says go ahead and walk, it's safe to walk. And you look both ways and there's no cars coming, and you say, okay, I'm going to go. So based on that information, you're really making an assessment of the probability that you're going to make it across the street, and that probability should be high before you're going to make that journey. Right? So you've got information that comes in, you update the probability, your assessment of the probability of an event taking place, and then you make a decision. So that's kind of how learning works, right? Isn't it? I mean, really everybody uses Bayes' theorem all the time. As soon as you get new information, there's a high probability of some outcome, then you make your actions based on that. Okay, so here's an example called Let's Make a Deal. Anybody played this game before? Seen this before? You have 3 doors. 1, 2, 3. And so there's a game show called Let's Make a Deal. And now the version with Wayne Brady, they never do this. But back in the 70s when the game show first started with Monty Hall, oftentimes towards the end of the game, a contestant would be brought before 3 curtains or 3 doors, and they'd say, look, behind one of the doors is a fabulous prize, a pile of gold or a Ferrari or something really cool. And behind the other 2 doors, there's donkeys. And unless you live in Lancaster County like I used to, donkeys just aren't worth that much money, unless, I guess, if you have a horse that you need a companion pet for. But the point is, you get 2 gag prizes. They're not going to give you those anyway. But behind one of the doors is a fabulous prize. And so you want the fabulous prize. And in fact, to get to this stage, Let's Make a Deal means that you're making deals kind of the whole time. The show starts out with people wearing crazy clothes and costumes. Monty Hall walks around and says, if you can produce 4 quarters and 3 paper clips and a stick of chewing gum, then I've got a deal for you. And so they look in their pockets, their purse, they ask their friends, anyone they can, and if they come up with that stuff, then they're in, and they start playing games and making deals with this guy. So they've traded up to this last game, and so they really want to win the game. Right? Everyone would want to win this game if you played it. So who wants to play the game right now? All right, you raised your hand first. So behind one of these doors is a fabulous prize. Behind the other two doors is our donkeys. So you pick a door. You pick door number 3. Okay, so what's Monty Hall going to do now? He picks door number 3. Monty Hall is going to do what?
That tells you like where that is affected.
He's going to open another door and say, look, what do you see here? That's a donkey. Okay, so there's a donkey behind door number 1. Who knows what's behind door number 2 or door number 3? But you've got the opportunity now to switch if you want or stay. Okay, so what's the best strategy here? Well, before you answer, let's see if we can do this quickly. I actually want to know what everybody thinks about this. So what's the best strategy? Should you switch? Should you stay? Or does it matter if you switch or stay?
This is kind of a popular, in terms of math, popular game show. Maybe you've seen this somewhere else in the past.
Okay, so we've got 28, 29, 30. Okay, so 45% of you said to switch, 36% said to stay, and 18% said it doesn't matter. Okay, so let's think about this. Well, let's see. Those of you who said to stay, why would you say to stay? I know 34% of you said that, so somebody should, yeah.
Like if you really don't love it, kind of second
Okay, maybe he's trying to sucker punch you somehow. So go with your first impression. Is that what you're thinking? Okay, any other ideas or reasons for why you'd want to stay?
I feel like people would not feel bad if they actually give up if they switch.
Okay, so if you switch and you lose, then you're going to feel bad. Okay. Are you going to feel bad if you stay and you lose? Probably. Yeah. Okay. Yeah. All right. Those of you that say it doesn't matter, why do you say it doesn't matter? Anybody? Maybe here's an argument. Maybe this explains it. You think that initially your chances of winning were 1 in 3, and now you're saying the chances of winning are 1 in 2. So what does it matter? Should you randomly pick between the doors that are left? I mean, that's essentially what you're saying. If you think that it doesn't matter, you should randomly pick. Okay. Well, it turns out the best thing to do is what 47% of you said, now 49%, that'll probably change, is to switch. In other words, we got information. What information do we have? We know that Monty Hall is never going to reveal the prize. He's always going to open a door. And we're going to assume that he randomly opens the door to show a donkey if he has that choice. Right? And so we have that information. We know the door that you picked. That's a piece of information. And we know the door that he opened. That's a piece of information. So if we use that information correctly, we can make ourselves much better off in terms of the probability that we're going to win. So if we switch, what's the probability that we're going to win?
It's a 50% chance that you could get one if you switch over.
Okay, so you're saying there's a 2/3 chance of winning if you switch? You're saying 50% chance if you switch? Okay. Anybody else have any ideas? So what's happening here is when you look at door number 1 and you see that, and you have 3 doors to choose from, what's the chance that you're going to pick the money, the prize? 1 out of 3, right? So that is when all probabilities are established. And it turns out that they don't change when the doors are open. So what does that mean? That means the probability that you initially pick the money is 1/3. And that does not change once the information is revealed. So when we get information, that's supposed to make us better off. And if you think that the chance that you win with your initial pick of door number 3, if you think that it goes from 1/3 to 1/2, well, you're wrong. The probability doesn't go from 1/3 to 1/2. It goes from 1/3 to 1/3. It stays at 1/3. Okay, the information that you had when you made the choice determines the probability, but how you use the other information is really where you're going to gain the benefit. Okay, so what's the probability then that you pick a donkey behind door number 3 with your initial pick? 2/3. Right, there's 2 donkeys, so there's 2 ways you can do that. And so if your strategy is to switch, you hope that you pick a donkey in the first place, because if you do, you're going to switch to the money, to the prize. So what's the chance of picking a donkey in the first place? It's 2/3. If your strategy is to switch, you're going to win 2/3 of the time. And if your strategy is to stay, you're going to win 1/3 of the time. Now, an interesting thing about this is that if you think, and 17% of you said that it doesn't matter, if you think that it doesn't matter and that it's 50-50 at that point, well, then you should randomly choose between your initial pick and the other door that's left. And it turns out if you do that randomly, flip a coin and randomly pick, you're going to win how often? Half the time. So if you think it's 50-50, it's almost like a self-fulfilling prophecy. You act like you think it's 50-50, it's going to be 50-50, turns out. Why? Because if you average 1/3 and 1/3 and 2/3, then you get 1/2. The probability that you win if you randomly select between those that are left is 1/2. So you said you were going to switch, young man there. Yes, you're going to switch, so you said. Well, good thing for you, because you won the money. Now you might be saying, "Oh, you just did that," but if you come over here to the week 3 folder, there's a Java applet. It says "Let's make a deal" applet. If you click on it, it's not going to open in whatever browser you have unless it supports Java. So go over to Internet Explorer, the old version of Internet Explorer. Paste that in, and you can play this game. Why is that not working? Okay, I guess it's not working anymore. Maybe they got too many complaints about the Java. All right. Well, there are other applets out there that you can do. I mean, it's a lot more fun than like Xbox. Anybody have an Xbox? Like to play Xbox? It's pretty good, but this is way more fun. You get one of these applets and you can just I don't want to search in the middle of class for one, but you should
check out this link. I'll update it so that it takes you to one that works. This was working last week. I don't know why it's not working now. Anyway, so can we use Bayes' theorem in order to show that this probability is really 2/3, 1/3? Yeah, we can. Let's say that M is equal to the event that Monty Hall opens door number 1. Okay, and we're going to say the probability that the money is behind door number 1 is equal to the probability that the money is behind door number 2, which is equal to the probability that the money is behind door number 3, and that's going to be 1/3. Okay, so call that the prior probability, and turns out that's going to be fixed. So now we want to know what's the probability that the money is behind door number 2, given that Monty Hall opens door number 1. Okay? Everybody clear on this, what we're saying? So he picked door number 3. Monty Hall opens door number 1. So given that that happens, what's the probability that the money is behind door number 2? Well, this is the probability that Monty Hall is going to open door number 1, given that the money is behind door number 2, times the prior probability that the money is behind door number 2. And all of that's divided by the probability that Monty Hall is going to open door number 1. Okay? So, what information do we have here that we already know? We know the probability of door number 2 having the money. That's 1/3. Do we know the probability that Monty Hall is going to open door number 1 given that the money is behind door number 2? And subsequently that door number 3 was picked. That's also information that's included in that. Do we know that? Well, we do know that, but before we write it down, let's write down the probability that Monty Hall is going to open door number 1. Okay, so probability of M. This is the following. Probability of M intersect that the money is behind door number 1, plus the probability of M intersect money's behind door number 2, plus the probability of M intersect that the money's behind door number 3. Okay, so why would I write all that? Because now I can write this as the probability that he opens door number 1 given that the money's behind door number 1 times the prior probability that the money's behind door number 1 plus the probability of M given the money's behind door number 2 times the prior probability that the money is behind door number 2 plus the probability of M given the money's behind door number 3 times the prior probability that the money's behind door number 3. Okay, so what do we know about the probability that he's going to open door number 1 if the money's behind door number 1 and door number 3 has been picked? All right, so tell me your name. Charles. Charles picked door number 3. If the money's behind door number 1, is Monty Hall going to open door number 1? No. So that probability is 0. So multiply 0 by probability of the money being behind door number 1, and we get 0 times 1/3. Okay? Given that the money is behind door number 2, and door number 3 was picked, what's the probability that Monty Hall is going to open door number 1? It's 100%, isn't it? Because we know he's not going to open door number 2 if the money's behind door number 2. So given the money's behind door number 2, there's a 100% chance he's going to open door number 1. And the prior probability of that is 1/3. Okay, now finally, what's the probability that he's going to open door number 1 given that the money's behind door number 3? So if the money's behind door number 3, he's got 2 donkeys, one behind door number 1, one behind door number 2, and he's going to randomly pick which one of those to open. So the probability of opening door number 1, given that the money's behind door number 2, given the money's behind door number 3 and door 3 was picked, that means there's a 1/2 chance that he's going to pick door number 1 and open that one. And so we get the probability that he's going to open door number 1 is 1/3 plus 1/6, which is 1/2. Okay, so now I can fill in the rest of this up here. I get 1/2 in the denominator, and in the numerator I have probability of m given $2 or $2, so it's going to be 1 times 1/3. And so when I calculate that, I get 2/3 is the chance that the money's behind door number 1. The money's behind door number 2, given what? That door 3 was picked and door 1 was open. So best thing to do is to switch. Does that mean you're going to win every time? No, but it means you're going to win 2/3 of the time when you switch, which is better than winning 1/3 of the time, and it's also better than winning 1/2 of the time. So when you come to understand things like this in their full detail, then you can make decisions that make you even better off. I mean, most people look at this and say, okay, it goes from 1/3 to 1/2. That's better, yeah? Okay, so if we operate based on that, then it doesn't matter if we switch or not. And so we'll randomly choose, so we're going to win half the time. Well, when you really understand what's going on, then you can double your chances of winning, go from 1/3 to 2/3. Okay, questions, comments? Okay, questions from homework number 5 then. Anybody tried homework number 5 yet? It's due on Thursday. What's that? The homework's due on Thursday, quiz due on Friday. That's how it's supposed to be anyway. Let's double check that because that would be bad. $19th. What? That's supposed to be due on Thursday. And that's due on Thursday. That's Friday. The quiz is right. Okay, I don't know why this says the 18th or the 19th. It should say the 18th. Because on the syllabus we've got Thursdays, but It's only 1%, so I don't care. I'll just leave it. I'll leave it. It's due Friday. If you want to, that's fine. Only because I already made the mistake and it's up there, and so it's due Friday. But the quiz is also due Friday. That's not going to be pushed to Saturday, because that's right. Yeah. 10/19, 11:59. Okay. So, any questions from the homework? If there's no questions from the homework, then we're done for the day. But really, this is your chance to ask questions. And I'll show you this how to do any of those homework problems.
Question about, I just wondering if how you know something like two variables separate.
Dependent or independent? Is there a specific question you want to look at from?
When I was looking at the question mentioned like how you know because you said information will be like how you know this is
Okay, so to check whether independent or variables are independent, are you talking about variables or events? Probably you're talking about events. Independent events. So we have A and B. If the probability of A intersect B is equal to the probability of A times the probability of B, they're independent of each other. That's how you check it. You can also check it by looking at the probability of A given B. Is that the same as the probability of A? If that's true, then they're independent. You can also check probability of B given A. That should be the same as the probability of B. In other words, if it doesn't matter whether A happens or not, probability of B is the same. So those would be independent. This is the one that you usually use because that one is usually the information that you have. Yeah. Okay, well, if there's no other questions then, I'll see you guys a week from today. 2 weeks from today we have an exam, so be ready for that. We're not going to meet in this classroom for that. I'll give you more information next week with regards to the exam.
Is the practice, like not the Learn Smart, because the homework with the practices, does that count for our grade?
No.
Or is that just extra?
It's just
practice?
extra stuff. Yeah.
Okay.
Extra.
Okay. Thank you.